Hello friends, I am Dr. M Agrawal, Assistant Professor, Department of Physics, Shri RLT College of Science, Akola. Our topic is nuclear physics. Here we discuss about alpha decay. Alpha decay. Alpha decay is a nuclear process in which alpha particle is spontaneously emitted from the parent nucleus and gives the daughter nucleus and release some energy. In alpha decay process, when atom emits alpha particle, its atomic number decreases by 2 and atomic mass number is decreases by 4 units. Thus, if X is a parent nucleus becomes Y daughter nucleus by the emission of alpha particle. Its general equation can be written as ZXA give rise to daughter nuclei Z minus 2 Y A minus 4 plus alpha particles twice He. For example, polonium 215 decays the alpha particles. It leads converted into lead 211. According to this equation, polonium 84P0 215, when it emits the alpha particles, it converted into the daughter nucleus, that is lead 8211 plus alpha particles 2He4. Properties of alpha particles. The alpha particle affects the photographic plate. It deflects by the electric and magnetic field. The alpha particle carries double the positive charge of proton, which is equal to the charge on helium nucleus. The alpha particle produce a fluorescence in certain substances like barium, uh, plutonium cyanide, and zinc sulfide. The alpha particle have the least penetration power but the greatest ionization power. The alpha particles scattered by the nuclei of heavy elements. Range of alpha particles, which is denoted by capital R. Most of the energy released in alpha decay is carried out by the alpha particle. When it allowed to incident on the matter, it will pass through the matter and collides with the molecules of the matter. During the collision, the energy of alpha particle will transfer to the molecule. Thus, alpha particle loses the energy of ionization. After collision, it will move in new direction and again collides with the other molecules and lose the energy. This process will continue till it loses or lost all the energy of ionization and finally it comes to rest. The maximum distance in which alpha particle loses its all the energy of ionization is called range of alpha particle. The range is generally expressed in centimeter. In air, it is 76 centimeter of mercury and its temperature is 15 degrees Celsius. It depends on the following factors, that is the initial energy of alpha particle, the initial velocity of alpha particles, nature of matter through which alpha particle passes, half-life period of alpha emitter. Next. Experimental determination of range of alpha particles. The experimental arrangement of determination of range of alpha particle is as shown in figure. It consists of ionization chamber. It is filled with suitable gas. It consists of plate P and metallic gauge G. They are placed parallel to each other and a constant potential difference is applied between them. A electrometer E is connected to the plate. It is used to measure ionization current. Here S is the source of alpha particle. When this particle enters in the chamber, it will ionize the gas and gives the ionization current. It can be measured with the help of electrometer. When the graph between distance traveled by the alpha particle and ionization current. From this it is clear that a particular distance r, ionization current decreases sharply. At a particular distance r, ionization current decreases sharply. The distance is called the range of alpha particle. Geiger has established a relation between the range of alpha particle and its velocity. According to him, the range of alpha particle is proportional to the cube of velocity of emission of alpha particle. That is, r is directly proportional to v cube. Geiger-Newton law. Geiger and Newton has established a relation between disintegration constant lambda and range of alpha particle. According to them, log lambda is equal to a plus b log r, where a and b are the constants. This is known as Geiger-Newton law. If we plot a graph between log r on x-axis and log lambda along y-axis, then we get a straight line. The slope of straight line gives the values of constant b, and its intercept on y-axis will give the value of constant a. From the graph, we can say that the disintegration constant lambda increases the range of alpha particle r, and range of alpha particle also increases. The disintegration constant is related with the half-life of the element by the relation lambda is equal to 0.693 upon T. Gamow theory of alpha decay. According to Gamow's theory of alpha decay, it lies inside the nucleus. R be the radius of nucleus surrounded by the potential barrier. Let particle is moving with the velocity v. During motion, it will collide with the wall of the potential barrier. Then, the frequency of collision is given by F is equal to V upon 4R. At each collision, there is some probability of transmission. If lambda is a disintegration constant, then lambda is equal to F twice Pt. If we put the value of F, then lambda is equal to V upon 4R into twice Pt, which is equal to lambda is equal to V upon twice R Pt, which is equation number 1. By solving the Schrodinger equation, we can find the value of Pt. That is d2 psi upon dx square plus twice m upon h cross square e minus v psi is equal to 0, which is equation number 2. Consider a rectangular potential barrier of width a and height v0. Consider three regions. Region 1, this region corresponds to the particle inside the nucleus. This particle is free and hence its potential energy V is equal to 0. Let a wave function psi is equal to psi 1, then therefore equation 2 can be written as d2 psi 1 upon dx square plus twice m upon h cross square e psi 1 is equal to 0. Putting twice m e upon h cross square is equal to k square, then equation becomes d2 psi 1 upon dx square plus k square psi 1 is equal to 0. This is the standard differential equation and its solution is given by psi 1 is equal to a to the power e I k x plus b e to the power minus I k x, which is equation number 3. Region 2 corresponds to the particle is in potential barrier. In this, v is equal to v0 and psi is equal to psi 2. Thus, equation 2 can be written as d2 psi 2 upon dx square plus twice m upon h cross square e minus v0 psi 2 is equal to 0. Then d2 psi 2 upon dx square plus twice m upon h cross square v0 minus e psi 2 is equal to 0. Putting the value of twice m upon h cross square v0 minus e is equal to beta square, then it becomes d2 psi 2 upon dx square minus beta square psi 2 is equal to 0. This is also a standard differential equation and its solution is given by psi 2 is equal to c e raised to power beta x plus d e raised to power minus beta x, which is equation number 4. Then region 3. In this region, particle is emitted outside the potential barrier. Then V is equal to 0 and psi is equal to psi 3. Putting this in equation number 2, then equation can be written as d2 psi 3 upon dx square plus twice m upon h square E psi 3 is equal to 0. Then equation becomes d2 psi 3 upon dx square plus k square psi 3 is equal to 0. Its solution is given by psi 3 is equal to g e to the power ikx plus h e to the power minus ikx. As alpha decay is irreversible process, therefore h e to the power minus ik is equal to 0. This value becomes 0. Therefore, psi 3 is equal to g e to the power ikx, which is equation number 5. Where a, b, c, d and g are the constant, their values can be determined by using boundary conditions. When x is equal to 0, then psi 1 is equal to psi 2 from this equation 3 and 4. Therefore, it becomes a e to the power 0 plus b e to the power 0 is equal to c e to the power 0 plus d e to the power 0. Then a plus b is equal to c plus d, equation number 6. When x is equal to 0, then d psi 1 upon dx is equal to d psi 2 upon dx, the differential equation 3 and 4. D psi 1 upon dx is equal to a e to the power ik plus b e to the power minus ikx minus ik. Therefore, it becomes d psi 1 upon dx is equal to ikx e to the power a e to the power ikx minus ik b e to the power minus ikx. Question number 7. d2 psi 2 upon dx is equal to beta c e to the power beta x minus beta d e to the power minus beta x, which is equation number 8. When x is equal to 0, d psi 1 upon dx is equal to d psi 2 upon dx. Using x is equal to 0 in equation number 7 and 8 and compare, you will get the equation a minus b is equal to beta upon ikc minus beta upon ikd, equation number 9. On adding the equation 6 and 9, you will get the equation a is equal to c in bracket 1 plus beta upon ik plus d in bracket 1 minus beta upon ik upon 2, which is equation number 10. Then when x is equal to a, then psi 2 is equal to psi 3. Using x is equal to a equation number 4 in equation number 4 and 5, on comparing, you will get the equation directly, that is c is equal to e to the power beta a plus d e to the power minus beta a is equal to g e to the power ika, which is equation number 11. On differential equation, equation number 5, we get d psi 3 upon dx is equal to ikg ikx, equation number 12. When x is equal to 0, d2 psi 2 upon dx is equal to d psi 3 upon dx. Using x is equal to a in equation 8 and 12, then comparing, you will get the equation beta c e to the power beta a minus beta d e to the power minus beta a, which is equal to ik g e to the power ika, which is equation number 30. On adding equation 11 and 12, then we get this equation, that is g is equal to 1 plus beta c e to the power beta a plus 1 minus beta d e to the power minus beta a upon 1 plus ik e raised to power ika, which is equation number 14. Therefore, from equation 10 and 14, we get these two equations, and as this probability of transmission, that is pt is equal to g upon a is equal to g upon a star. By using the above equation and solving, we get pt is equal to e to the power minus 2 beta a. As beta is equal to twice m upon h cross square v0 minus e to whole to the bracket 1 by 2. Using the value of beta in above equation, then you will get pt is equal to e to the power minus 2 in bracket twice m upon h cross square v0 minus e whole bracket 1 by 2 in a. In determination of pt, we have to consider a rectangular potential barrier, but in actual it is a circular barrier. Hence, above equation can be modified as pt is equal to minus twice upon e raised to power minus twice upon h cross integration 0 to a in bracket twice m v0 minus e whole bracket raised to power 1 by 2 into dr. Using in equation 1, disintegration constant lambda is equal to v upon twice r e to the power minus 2 upon h cross integration 0 to a twice m v0 minus e raised to power 1 by 2 into dr. Using this relation, this integration constant lambda of element can be determined. Thank you.